Okay, so welcome back. Today the goal is to talk about part 2 in our series on designing and building a simple constant current 0 to 5 amp DC load circuit. And in part 1 we went through LT Spice and did some basic design. In this video we're going to do what I've got here, which is basically breadboard it, choose some components, put them together and see if they work. And this is a good exercise because we're going to get into thermals. That we're going to be dissipating, 25 to 50 watts. We're going to see how you can choose devices that can handle that and how you can cool them. And as you can see here, I've got basically my control circuit down here. I've got the output circuit. This is the part that actually draws the current. I've got a power supply, which is set at 10 volts, and it's not drawing any current. And basically what I can do is I can adjust this potentiometer to select how much current I want to draw from this power supply, and it will be a constant DC current, almost independent of what voltage I set on this. It will maintain a constant current. And I can show you. I'll start to turn it on, the potentiometer, and I'm up to 0.2 amps. Let's bring it up to 1 amp. And I'm turning the potentiometer to get just at 1 amp. And there you go. Now you can see if I adjust this voltage, that will maintain 1 amp. So I can bring it down, 9, 8, and I can bring it up, 10, 11. So that's the goal of this, to figure out how we can develop a constant current DC load. Now, what we're going to do now is jump back into LT Spice and show you some of the thought processes and how I chose these devices. We're going to look at some of the thermals, some of the capabilities of these devices you need to consider, and some of the challenges you need to consider when buying these devices in terms of accuracy and everything else. So let's jump over into LT Spice and get into some of the details. Okay, so here we are back in LT Spice, and as you'll recall from part 1 in this series, I encourage you, if you haven't looked at part 1, we go through some of the basic design concepts and what circuit we're designing here. This is basically the same circuit. The difference is that I've actually chosen some components based on the requirements of this circuit. And what I'll do is I'll briefly go through some of the thought process I use to pick the components. Here we have the control circuit that basically controls the power circuit. And here's the power circuit. And it's very simple. It only includes a MOSFET and a 1 ohm resistor. And the goal here is to connect up an external device. In this case, we're using an external power supply. And this control circuit will control how much constant current flows through this MOSFET and resistor. And we can set this from 0 to 5 amps. All right. So basically this op amp senses the voltage across the resistor, and whatever voltage we put in here, it matches that to this voltage, so that, for example, if we put 5 volts in from our power supply over here, it will correspond to 5 volts across this resistor, and since it's a 1 ohm resistor, we'll get 5 amps. So that's the basic functionality of this. Now, starting on the left, what I've done is I basically had an old laptop AC to DC adapter that I'm going to use to power this, and it's 20 volts. Now, in the previous video, we said you can use, something like 12, 15 volts to power this. I'm just going to use 20 volts because it's what I had lying around. Now, this value of VCC that you apply to this op amp is important because this gate has to have enough voltage behind it to generate enough voltage to operate this MOSFET in the range you're going to need. Now, we said this is going to go up to a maximum of 5 amps in the circuit, which means this voltage at this node is going to be a maximum of 5 volts. And we know that the on voltage to turn on a MOSFET is something like 3, 4, 5 volts, something like that. So we know right off that this gate voltage is going to have to be about 5 for the gate source voltage plus 5 for this resistor. So right there, you're going to need about 10 volts coming out of this gate in order to turn this on and make it work. So we've got 20. If you look at the op amp data sheet, it's up to 30 something. I'm using an LM358 I had lying around. So we're good there. So basically on this control circuit, I've just got a laptop adapter coming in with 20 volts. Now the goal here is this is the potentiometer I'm going to use. And I want this to apply 0 to 5 volts into this op amp so that it can generate 0 to 5 volts across this resistor, thereby pushing 0 to 5 amps in this circuit. So if I want 0 to 5 volts coming in here, and I've got 20 volts here, I'm going to need a 15K dropping resistor if I've got a 5K potentiometer, all right? 5 over 5 plus 15, which is 5 over 20, gives you 5 volts on this wiper out of the potentiometer. So basically I'm using a 5K ohm potentiometer in series with a 15K dropping resistor, and that will give me the 0 to 5 volts here, okay? And again, I'm using an LM358 solely because I had it lying around. Now what we're going to talk about is choosing this potentiometer. There's some choices, and when we go back to the bench, we'll talk about some of the options that you may want to consider. Now, on the power circuit, I've basically got two components. I've got this MOSFET and I've got this resistor. Now, these are going to be the interesting things to choose because there are some things you need to consider here. The first thing we're going to look at is this MOSFET. Now, I originally had thrown in an IRF 510, and the reason was that it's the first thing I grabbed out of the box. It turns out that there are some better choices if we're going to have 5 amps flowing through this circuit. If you look at the data sheet for this, what I've ultimately chosen, I'm using an IRF 530 instead of a 510. And the reason is, there's a few reasons why. This can handle continuous drain current at case temperature for 100 degrees C of 10 amps. While the previous one, the IRF 510, which is this, only handles 4 amps, okay? So right there, that's a good reason to not use the 510 if we're going to go up to 5 amps, right? Now, the other thing you need to consider on these is the operating junction temperature, and they're both the same for both devices. And that's up to 175 degrees C. So that's going to be important when we decide how to cool this thing and what temperatures to avoid. Now, one other important thing we're going to need to consider here is the thermal parameters of the device. And this is for the IRF 530. And if you look down here, you can see the maximum junction to case thermal resistance is 1.7 degrees C per watt. This has a better temperature characteristic than the 510. If you go down with the 510 and look at the thermal, it's 3.5 degrees C per watt, which just means that this 510 will get hotter for each watt dissipated inside the device, okay? So if you dissipate 1 watt in this MOSFET, the temperature will rise 3.5 degrees C. And if you dissipate 10 watts, it'll be 30 degrees C. While with the other one, it'll be 10 watts is only 17 degrees centigrade rise in temperature. So that'll be important. So again, that's why I decided to choose the IRF 530. It's got a better set of specifications. It allows us to do 5 amps, and the thermal response is a little bit better. Now, one of the important things we need to consider, and we're going to take a look in LT Spice about this issue, is if we're going to be using like 5 amps flowing through a electronic circuit, we really have to start worrying about thermals. And one of the key considerations is you can see that we are designing this at this point for an external power supply of 10 volts, and ultimately the maximum it will deliver is 5 amps through the circuit. So 10 times 5 means 50 watts, okay? 50 watts is a lot of energy to dissipate, which means there's going to be a lot of temperature rises on these devices. They're both going to see 5 amps, and that can be a lot of power, and you're going to have to design for it. So the first thing I want to do is I want to find out how many watts, how much power is going to be dissipated by this MOSFET at the maximum 5 amps. So I can do Alt, left click, and you can see 25 watts is going to be dissipated by this MOSFET at 5 amps. And if you do a sweep, which I think I did in the previous video, you can see it's less than 25 as you go from 0 to 5, and then when it gets up to 5 amps, the maximum is 25 watts. So we have to plan for 25 watts being dissipated in this MOSFET, which means we have to figure out what are the temperatures going to be with 25 watts dissipated. And the same thing for this resistor. If this is 25 watts and there's a total 50 watts being dissipated, 10 times 5, then this is going to be 25 also. So we're going to have a total 50 watts dissipated, 25 in each device. So we're going to have to make some plans here to figure out how to dissipate all that energy. Okay, so let's look at this IRF 530 MOSFET and start thinking about if it's going to dissipate 25 watts, what do we have to be worried about? Well, if you look up here on the top right, it says features 175 degrees C operating temperature. And if you look down here, it says thermal maximum, somewhere it says maximum operating junction temperature can go from minus 55 to plus 175 degrees C. So in a couple of places, they imply that the internals of this MOSFET can go no higher than 175 degrees centigrade. So that's a good bit of data. Now, generally, I don't want to go anywhere near that. You know, I would like to keep it down 100 degrees C, something like that, which, you know, if you know anything about computers and CPUs and GPUs, they generally tend to limit their temperatures to around 100 degrees C. And at that point, they start to throttle and turn fans on and stuff like that. So I tend to like to stay around 100 degrees C, and I don't want to get anywhere close to that. It's up to you how dangerous you want to be. So we know that we're going to want to manage this temperature on this MOSFET so it's down, in my case, around 100 degrees C maximum, and we know it's going to be 25 watts. Now, if you take this MOSFET and you put it on your bench and you measure the temperature, what's the temperature going to be? Well, it's going to be whatever the ambient is, which is probably 75 degrees Fahrenheit or 25 degrees C. So it's going to start out at ambient temperature, 25. Let's call it 25 degrees centigrade. So if I turn on this MOSFET and apply power to it, and it dissipates 1 watt, what's that going to do? Well, it's obviously going to warm it up. It's going to get warmer than 25 degrees C. It's going to start at 25, and it's going to get warmer. The question is, how much warmer will it get? If I put 1 watt through it, how much warmer will it get than the normal 25 degrees C? Which says, you know, I wish there was a number that defined, you know, if I put in 1 watt, what temperature rise will that correspond to? So 1 watt, will it go up to 28 degrees C? Will it go up to 30 degrees C above the normal starting ambient? Well, it turns out there is a number that explains exactly or describes exactly that. And if we scroll down here, it's called the thermal resistance. And it defines the maximum junction to case degrees centigrade per watt. So for this IRF 530, it will go up 1.7 degrees centigrade for every watt that you dissipate inside, which means that the internal temperature inside of this MOSFET, called the junction, where the stuff actually happens inside this case, that will be, for every watt you dissipate, that will be 1.7 degrees hotter than this case, which is this tab, this metal tab, okay? So you dissipate 1 watt, the junction inside will be 1.7 degrees C hotter than the outside, all right? So that's really good to know. If I know what the temperature of the outside is, I'll know that for every watt, the inside is 1.7 degrees C hotter. So for, if I'm dissipating 10 watts, the internals, which I can't measure, are going to be 10 times 1.7, or 17 degrees C hotter for 10 watts than the outside case. And what I can do is I can say, well, okay, if the case is that much hotter, then I can figure out what all the temperatures need to be for my heat sink and ambient and everything else. So that's a really good bit of information. So now there's one other interesting bit of information in this table. And on the top here it says maximum junction to ambient. And that's a huge number, 62 degrees C per watt, which tells me if I dissipate 1 watt in this MOSFET, the junction will be 62 degrees C hotter than the ambient. So if the ambient is 25 degrees C, that means it's going to be a junction temperature of 87 degrees centigrade. So if I generate 1 watt inside this MOSFET and don't cool it with anything, I just let it stand out in ambient, it's going to be 87 degrees C inside this junction with just dissipating 1 watt. So if I dissipate 10 watts, you can imagine the temperature, okay? How many degrees C for 10 watts? 62 degrees C for 1. So this thing is going to melt if I dissipate 10 watts and just leave it without cooling. So we're going to use that 1.7 degrees C, and we're going to figure out what the temperature is going to be on our entire power circuit. So here I've made an Excel spreadsheet, and what I'm going to do is I'm going to assume I've got my MOSFET and I am dissipating 1 watt in the MOSFET, okay? Well, we know that the difference in temperature between the internals of the MOSFET and the case are going to be 1.7 degrees C for every watt. And since I have 1 watt, there's going to be a 1.7 degrees C difference between the internals and the outside case. Okay, we can do the same thing with the thermal difference between the case and whatever heat sink you hook it up to. And we'll talk about this on the bench. We'll look at the actual devices. But if you screw this MOSFET onto a heat sink and apply some thermal compound, I've got a number here which says, ballpark is you might get a 0.5 degrees C rise of the heat sink over the case for every watt, which means if I have a watt going through the MOSFET, then the heat sink is going to be, or the case is going to be 0.5 degrees C hotter than the heat sink if I'm passing 1 watt, okay? And the same thing for the heat sink to the ambient. It's difficult for the heat sink to dissipate heat to the ambient air, so there's a bigger number, which means there's a bigger difference between the heat sink temperature and the normal ambient temperature. So that number is going to be bigger. I put in a 3 there to say the heat sink is 3 degrees C warmer than the ambient temperature because it's more difficult to transfer heat away from the heat sink into the ambient. So here's just some ballpark. We know this is good, this 1.7. I've used some other numbers. So it says if I put 1 watt into the MOSFET, and I have over here, I've got a 25 degrees C ambient, then my heat sink will be 28 degrees C, okay, because there's 3 degrees C per watt. So, and then the case will be 28.5 since there's a 0.5 degrees C per watt, and the junction will be 30. So the ambient is 25 and the heat sink's a little warmer, the case is a little warmer, and the junction is a little over 5 degrees warmer if I pass 1 watt through there. So we said that the junction can be, according to the spec sheet, the data sheet, 175 degrees C, so we're way, way under that, so we're fine. Now let's change this to 25 watts. Wow, that's a big difference. Okay, I've got a 25 degrees C ambient. The heat sink is now 75 degrees C hotter than the ambient because we had a number of 3 degrees C per watt for the heat sink to ambient. That's 75. And then the case is another 13 degrees warmer than that. And then the internal junction is 40 or 52 degrees warmer than that. So now we're getting up really close. If we pass 25 watts through that MOSFET and we're using these numbers, that junction is going to get really warm. It's up near the 175 and it's getting into danger territory. So now we got to say, wait a minute, what are we going to do? There's not much we can do about the junction to case temperature. That's part of the internal design of the MOSFET. Case to heat sink, this is pretty low. There's a pretty good transfer of heat because this is a low number. So the heat sink to ambient, that tells us we need a really good heat sink that has a ratio a lot less than 3. So let's assume, and I've done some tests, and I think a good heat sink might give you a 1 degrees C per watt. So if you look now you're getting a junction temperature down to 105 degrees C, which is in the decent territory, okay? So this is the kind of process you need to go through. You figure out what your ambient is and how much warmer each component is based on their characteristics. And you want to make sure you keep the junction temperature way below this 175. And I think this is a really good junction temperature. So what this tells us is we need to find a heat sink and maybe a fan combination that will keep our case temperatures down in the 60 degrees C range, okay? And we're going to do some actual measurements. I've actually done some measurements, and if I put a small heat sink on, my case temperature is going to be 110, which is going to be really warm for the junction. But if I put a large heat sink, it's going to be more in the 50 to 60 degrees C, which means, we're going to be in the 100 degrees C junction temperature. So we'll take a look on the bench about, what we chose for components and what we expect and what we measure for actual temperatures so we can see where we are. Okay, so now we're back with our circuit. You can see I've got the power circuit over here. I got a fan running. I've got a input power supply, which is what I'm going to draw the constant current from. And I've got the control circuit down here. Now, I'm going to talk about some of the components I chose and why I chose them. In the control circuit, you can see I've got a potentiometer here. And this is a relatively expensive potentiometer. Now, there's a couple things you can choose. If you go on Amazon, for example, you will find tons of these cheap potentiometers, less than $1 a piece. You'll probably get a big assortment of them. The other one, what I chose, is this more precision 10-turn pot. And I got this from Mouser or DigiKey. These are relatively expensive. I think they're like $8 a piece. These are maybe $1 a piece, these cheap ones. Personally, I despise these cheap little potentiometers, the single turn potentiometers. You know, you get what you pay for. It might work fine for you. I have nothing but problems with them. They're unreliable. The resistance bounces around as you turn it. These are very reliable. So I suggest you try DigiKey or Mouser and spend a few bucks on these. They're really nice and nice and solid when you adjust. Like in this case, we're going to go from 0 to 5 volts. Nice and clean, and you can adjust it very accurately. Now, another thing we need to talk about is heat sinks. You can see I've got my MOSFET and my 1 ohm resistor mounted on a heat sink. Now you can choose whatever you want. You can start out with something like this, a little tiny one. Now when we did our Excel spreadsheet showing the different thermal resistances, this kind of device might give you a thermal resistance from heatsink to ambient of around 3, while this with the fan might give you around 1. And I've done some tests and it seems like those are reasonable numbers for the different heat sinks. So this really is not going to work for something like this, because you saw with a ratio of 3, you're going to get MOSFET junction temperatures up in the 150 degrees C. So that's why I opted to spend some money on this big heat sink and mount both the devices. And it gives us actually better than we predicted on the spreadsheet. So we'll talk about that in a bit. So again, heat sinks, the bigger the better. And if you can get it, this little 12 volt fan, nice and quiet, and it cools it really well. Now, the next thing we need to talk about is, in order to assure that you have some good heat transfer from your heat sink to the case of your device, on each of these, I've added some of this thermal compound. And this is very, you know, if you're familiar with CPUs and GPUs and computer electronics where you add thermal compound to a CPU in the heatsink, this is, for example, Arctic Silver, which is a very common one. And I've used that to ensure a really good heat transfer from the case of each of these devices to the heatsink. So you just squirt a little bit on and you're good to go. Now, the other thing I want to talk about is this resistor. Now, I just completed a video talking about power resistors, the negatives of power resistors. And the problem is we are looking for an accurate 1 ohm resistor, which this one is. However, if you go on to Amazon, you will see a ton of unbranded resistors like these that look exactly like the really good ones. But honestly, if you look at my previous video on power resistors, the accuracy can be absolutely horrendous when you start to load these things up. This other one I had, if it was a 1 ohm resistor, if you put it up around 25% of its rated watts, the resistance is way out of range. It's up in the 30%, off by 30%. So it's really, really bad. So this is another resistor just like that, where the accuracy is really bad as you start to load it up. And generally, if you go on Amazon and you find a manufacturer that has no spreadsheets and no website, those are the ones you got to be careful of. So I strongly recommend you don't fall for, especially if you're going to do something you need accuracy. What I did is I went on Mouser or DigiKey, and you can also get these ceramic wire rounds. This is a 5% accuracy, which isn't quite what we need. But this one is a 1% accurate, and it is rock solid, and I strongly recommend. They're about $8 a piece, I think, but they're really, really good and very accurate. And this is just an example. This is the resistor I got on from Mouser, I think. It's Vishay Dale. Vishay is a very big name in electronics, of course. Excellent stability in operation, less than 1% change in resistance, and it's got actual spec sheets, and you can look at all the numbers, but it really rock solid in my experience. Okay, so now what we're going to do is run the circuit and run it up to 5 amps, which means 25 watts dissipation across the MOSFET and the resistor. And what I'm going to do is I'm going to measure. I've got a thermocouple here going to this multimeter. You can see the ambient is 24 degrees C. And I'm going to measure the temperature of the case of the MOSFET. And I've got the thermocouple right down on the case, as close as I can make it. And what I'm going to do is measure the temperature over time. As you recall from our spreadsheet, we said it'll probably be around 50 or 60 degrees centigrade with 25 watts, which means that the junction is going to be up a bit over 100 degrees C, which is fine. So what I'm going to do is I'm going to turn up this potentiometer until I get 5 amps. And this is a multi-turn pot, so you can see I got to turn it about 10 times, and the maximum should be about 5 amps. 4.78, 9. So we're right at 5 amps constant current. You can see the case now over here is about 32 degrees centigrade. And we're fixed at 5 amps. And you can see it's slowly going up. Again, I've got the fan going and I've got this big heat sink. And we'll give it some time and see what the final temperature is. Okay, so here we are after maybe 10 minutes, a little bit longer. And you can see the case temperature of the MOSFET is about what we expected. It's about 60, 61 degrees. It goes up very, very slowly. So, but at least we've got a good idea that our guess of 1 degree C per watt for the big heat sink is pretty reasonable. And for the small one, 3 is probably a good ballpark. Although you can go online, you can search and find the thermal resistance of the different devices, but at least it gives us a good ballpark. So we're pretty happy now. 60 degrees C for the case means the junction's going to be just around 100 C, which is fine. And so now we're pretty good in our design. We've got the components, and we can see that as you vary the voltage, you're not changing the current at all. It's staying fixed. The problem is if you go up in voltage, and this is one of the limitations of the circuit, as you go up in voltage, keep in mind you're applying a lot more power to this MOSFET and the resistor. So you're quickly going to get temperatures going up very quickly. So this is a limited circuit in that it can only go a fairly narrow range of external devices like this power supply. You might go up, go between 8 to 12 volts, but if you get much below 8, you're going to clamp it. You won't be able to get 5 amps. And if you go much above 12 or so, the power dissipation is going to be huge, and you're going to start to overheat things. So you got to be careful in your design, but at least this is a good methodology you can use. So anyway, hope that helps. Take care and have a really good day. Thanks.